and welcome back to the final video that I have to make. Also the final video on this chapter on reaction rate. Don't you just love this topic? It's so short and easy. How many videos did I make for the last chapter? I don't know, I didn't count. But anyway, I'll be very happy to take a break from talking to the screen for a while, I think. So we're going to end this chapter on catalysts and a discussion on how a catalyst can increase the reaction rate. Not in a lot of details. This is a definition of catalysts. So basically, catalysts are substances that provide an alternative reaction pathway with a lower activation energy. So the main purpose of a catalyst is to lower the activation energy barrier of a chemical reaction and therefore increase the rate of that reaction. Beside that, I don't think catalysts have a lot of in common. So one catalyst and another catalyst can be very, very different in the chemical compositions and how they actually achieve the alternative reaction pathway. It is a very fascinating field of study, catalysts, and quite difficult. So this is active energy profile diagram again, and you can use the energy profile diagram to represent how a catalyst works. So if you have a reaction, we have reaction going to product. So the activation energy without catalyst is going to be this high. So you need this much energy to be absorbed in order to get to the transition state. However, if there is a catalyst, essentially it provides an alternative reaction pathway and the activation energy is a lot lower. So the peak that you need to reach is a lot lower. I do want to point out that regardless of whether you use a catalyst or not, or using a catalyst is not going to change the amount of energy that is either absorbed or released overall. So the delta H of a chemical reaction remains the same, regardless of whether you use a catalyst or not, as represented in this diagram. The other important point to note is that catalysts are not consumed in the chemical reactions. They are neither the reactant or the product, so they're just there to help, so they won't get consumed, which is a very good thing about catalysts as well, is that they're reusable. So I probably should write it here. So they are, so you can use the same catalyst for multiple times for different the same reactants but different times. I don't even know what I'm talking about anymore. Anyway, catalysts are reusable. Okay. You can also represent the effect of catalyst using the Maxwell-Boltzmann energy distribution. So this is the difference between a catalyst and temperature, is that temperature, when you increase the temperature, you're changing the shape of the energy distribution, whereas when you apply a catalyst, the shape doesn't change because the average kinetic energies of particles still remain the same. The only thing that you've done here is that you've lowered the requirement. So the activation energy in an uncatalyzed reaction could be up here. If you add a catalyst, you just lower that requirement, and so you get these extra particles that now meet the activation energy barrier because the barrier has been lowered. So I passed math 50%, whereas pass math 40%. No extra effort from students. Okay, so by providing an alternative reaction pathway with a lower activation energy barrier, catalyst increases. So this is another thing that also increases the proportion of particles that have enough energy to overcome the activation energy barrier. And of course, that increases the rate of reaction. So this is the textbook explanation of the effect of a catalyst. So we can now finish this, what is this called? Chart? Graph? I like diagram. I do a lot of visual summary, I think. Maybe not enough. But yeah, so catalyst essentially only affects the proportion of collisions with enough energy to overcome the barrier, but it doesn't affect the frequency of collision. I think you can just remember this summary and you're probably okay. All right, I think I already talked about this before, but just to emphasize this one more time, the difference between increasing temperature and using a catalyst. So if you have, let's say that's 25 degrees, and let's say this is the activation energy barrier, when you increase the temperature from say 25 to 50 degrees, what you're doing is you're changing the distribution of energy, but the activation energy doesn't change, and then you get all of these extra particles that now can meet activation energy barrier. So you're increasing the proportion of particles that can meet the activation energy barrier, by increasing the energy that they have. So that's increasing in temperature. Now, if I have a catalyst, so if I use the same thing, so if I have 25 degree here, that's supposed to say 25 degree, not 250, by the way. If you have a catalyst, so if the EA, let's try to match this EA. So if the EA is here, then when you have a catalyst, it just lowers the EA without needing to increase the temperature. Now, the decision on whether to use high temperature or use a catalyst to increase the rate of reaction really depends on how expensive the catalyst may be and what temperature do you need. And also one extra thing that we're going to talk about in chapter 8, which will take 3 weeks to finish. We'll see. Okay, so basically you lower the activation energy, and this is the added proportion of particles that can now overcome the activation energy barrier. So in this particular example, it looks like catalyst is having a greater effect. It obviously depends on the catalyst as well as the temperature. Okay, one final thing. I don't even know how much details I'm supposed to go into this because the study design has been pretty vague on what they want. I think you just need to know the bare minimum, which is just the definitions of the different types of catalysts. So the first type is homogeneous catalyst. So homo prefix just means same. So homogeneous catalysts are catalysts that have the same states as the reactants and products. So I have an example here. You by no means need to remember this example. But let's say if you look at this, so the reactant is hydrogen peroxide aqueous, and this reaction can use iodide ion as the catalyst, which is also aqueous. So this is a homogeneous catalyst. The good thing about homogeneous catalysts is that they can be mixed really thoroughly with the reactants because they have the same state. Most of the time they both like aqueous. But the issue, of course, is it's a little bit harder to recover the catalyst once the reaction is finished because if like in this case it's mixed with the product, so it takes a little bit of time to separate the two if you want to reuse the catalyst. Otherwise, you're just going to dilute the solution over time. This is an example of how a catalyst could actually lower the activation energy barrier. So in this case, you have a multi-step energy profile diagram. You don't really need to worry too much about this. I don't even know why I leave this example here. I think it's just to show you how you can have an alternative reaction pathway. So in this particular example, the catalyst splits the reaction into two intermediate steps, but overall they still have lower activation energy barriers than the non-catalyzed reaction. Anyway, so a new pathway is formed, and then all steps involved in the new pathway have a lower activation energy than the original. And this is also very interesting because in this particular case of the homogeneous catalyst, it actually did participate in the first reaction and then it gets reformed in the second one. So overall, it's still not consumed, which is why it still fits the definition of a catalyst. But it does actually participate in the reaction at one point. So the iodide that you start off with is probably not the iodide that you finish with. The other type of catalysts are heterogeneous catalysts, and I think you can guess what they would mean. They basically have a different state as the reactants. So this is, I think the example is the fuel cells catalyst that we talk about, when the catalyst would be embedded into the electrode. So the catalysts are solid, but the reactants tend to be gases. So you have different states. Obviously, the good thing about this is it's very easy to separate the catalyst from the reactants if you want to reuse the catalyst in other situations. But it is a little bit harder to ensure that all of the reactants have contact to the catalyst. So most of the time when you have heterogeneous catalysts, they are there to serve as a surface for the reactants to adsorb or anchor or stick to. So in this case, we're talking about a catalyst for addition reactions of alkene, which is coming back next unit. Did we learn this last year? I can't remember. I think we did. But it is coming back. This is normally nickel. It's a classic catalyst for hydrogenation of alkene, which is so nickel is a metal, by the way. So the catalyst causes bond to stretch and break. Activation energy is lower as the bond's already under tension. So again, this is optional. Please don't worry too much about this part of the notes. I think the main thing to understand when you think about a heterogeneous catalyst is because it serves as a surface for the reactant to adhere to, it makes it easier for the correct orientation or even the collision to happen, because if one of the reactants are not moving so quickly, it will be easier for the collision to occur between them, because you kind of stop one of them and wait for the other one to come, if you will. This is another example of platinum catalyst, which is used a lot in a fuel cell. Of course, the issue with platinum catalysts is that they're fairly expensive, and that increases the cost of fuel cells significantly, but they're very good. Yeah, so the main thing with heterogeneous catalysts is you want to make sure that every reactant can have access to the catalyst. If the catalyst is a solid, then you want to maximize the surface area, so that all the reactants, be it liquid or gas, could actually come into contact with the catalyst. So if you think about, I don't know why I keep these photos in my slide for so many years, but I just find this hilarious somehow. I probably should fix this. Is you really want to maximize surface area. So anything that's porous or it's like a mesh, that's always going to be a better catalyst, because you can maximize the contact between the catalyst and the reactant. So this is not a very good catalyst for that particular purpose. And lastly, we're gonna have to create an entire category for enzymes, which are biological catalysts, and they essentially speed up reactions in the cells. I think we're going to talk about enzymes a little bit in Unit 4, but a lot of it has been removed from this year curriculum in particular. But anyway, that is the end of this chapter. Thank you.